Welcome to the 17th lecture. We will continue studying Class A amplifiers in this lecture. In 16th lecture, we started power amplifiers. We know that power amplifiers are amplifiers that use to drive speakers, the high power load at the output, and in a cascade of a multi-stage amplifier, these are the last stage amplifiers. So we started studying class A amplifiers in our last lecture. We will continue studying the same amplifier in this lecture. DC quiescent power is the first topic we will study, and then we will study the output power, maximum output power, and the third thing that we will study in this lecture is the efficiency of a class A amplifier. So let's start this short lecture. The DC quiescent power is the Q point power that is supplied by a class A amplifier, and that is the VCEQ. If this is the output segment of a class A amplifier, VCEQ is the DC voltage present at the output, the collector terminal, times the ICQ, the current that flows through the collector terminal and then it flows into the collector, that flows in through the collector resistor and then flows into the collector terminal, is ICQ. This product is called quiescent power, DC quiescent power. So this is the first term we will study here. Let's call it equation number 1. So we'll actually study one more equation before we compute the efficiency of a class A amplifier. Right, so the DC quiescent power PDQ is the first term or the first item we have studied up till now. The second thing is, for a common emitter amplifier, we will study the maximum output power, VC max. Then this is the maximum output AC power. In fact, what's that? AC power, VC max, is ICQ times RC, is ICQ times RC. If we start from VCEQ, and this is the reference level for the AC to swing at the output, what is the max that, suppose this is, let's write here, suppose the output has a DC level VCEQ at which it is going to have a swing like this. So what is the maximum voltage that this swing can reach? Of course, this is VCC. The supplied voltage is the max swing that it can reach. So how would you do? How would you calculate that VC max? That would be, in fact, VCC is the voltage drop here, the voltage of this terminal with respect to ground plus the voltage drop here. So if we add these two voltages, the voltage drop across resistor RC and the voltage of the collector terminal with respect to ground, if we add these two DC voltages, it becomes VCC. So this is the starting point for the basis point for this output AC to swing, and this is the margin it has on the positive side. So what's that margin? It cannot exceed VCC. So if VCC is this voltage drop plus VCE, then the margin would be this IC, VCC minus the VCQ. So this ICRC is the margin. If we can write it somewhere like this, VCC is ICQ RC plus the voltage VCEQ. So if we take VCEQ on the other side of the equation, VCC minus VCQ, so we are left with ICQ RC, and this is the margin that this output AC will have to swing on the positive side. So this is the max voltage ICQ RC. This is actually the peak value of the AC signal. We have studied in our earlier courses, like in LCA, linear circuit analysis, that peak voltage VP of a sinusoidal voltage is the maximum voltage attained on either the positive side or the minimum voltage achieved on the negative side. So it gives us a peak either on the positive or on the negative side, which actually the same, which are same in the magnitude. So this is actually VC max is the peak voltage that this output is the peak value that this output AC voltage can have. Of course, not, since it cannot go beyond VCC, therefore it has to be ICQ RC, right? So, or in other words, the max current that on the same lines, it can be shown that max current IC is VCEQ over RC. So if you multiply the two, this one equation number, let's call it equation number 2 and equation number 3, if you multiply the two, the answer is of course power. Then P out is VC max times R max. So if we put an RMS here, then RMS means that if we are given the peak voltage and it is a sinusoidal wave, the RMS would be of course 0.707 times the peak value. We know that. So 0.707 times the VC max times 0.707 times the IC max. So 0.7 times 0.7 is 0.5. So it becomes this. So it comes out to be equation number 4. Equation number 4 is 0.5 ICQ times VCEQ. So this is the output power, the RMS value of the output power, the max output power. And before that, in equation number 1, we have studied the DQ, the DC quiescent power. What should be? Then now it's a time to compute one more power, that is the power supplied by the source. That would be the last term that we will study. This is the DC power supplied by the source. Of course, that will be VCC IC. What's that power? This VCC, the power that this VCC is supplying, VCC times IC. It is supplying one more current, IP, but we generally neglect that because IP is much smaller than IC. So since VCC is supplying two currents, ICQ plus plus IP. But since IP is very small, it's much smaller compared to IC, therefore we neglect that and we'll consider only IC. So VCC times IC is the max ICQ, is the max power that it is supplying. It's the max DC power that the DC source is supplying. So DC power can also be written as, since we are bound to bias this in the middle of the VCC. So VCEQ has to be 2 times VCEQ has to be VCC by 2, or VCC is 2 times VCEQ. So now we are all set. In fact, this is equation number 5. This is equation number 5. So we are all set. What we'll do is we are going to divide equation number 4 by 5. Equation number 4 divided by equation number 5. That will give us the efficiency, the max output power that we can supply to the load divided by the input power that we are drawing from the power supply. So this is 0.5 ICQ VCEQ, and the max DC input power that we are taking from the source is 2 times this VCEQ IC. So now we have this VCEQ, this cancels with this VC, IC cancels with this IC, and eta, which is efficiency, eta is 0.25. So this means that class A amplifier is at the most 25% efficient. So this is the max efficiency of a class A amplifier. What does the efficiency means? The power that this amplifier is supplying to the load. What is the ratio? We have a load here, this load RL. The power that this amplifier is supplying to this load divided by the power it is drawing from the input DC source. So that ratio multiplied by 100 should be the percentage of the percentage giving us the efficiency. So this is 25%, very small efficiency. We'll see that this efficiency is even smaller for other classes of amplifiers in our upcoming lectures. Thank you. That's all for ECD17.